Hello everyone! In this video we will continue to examine topic 5.2, the heating effect of electric currents, and in particular we will begin to unpack multi-resistor circuits. In particular, multi-resistor circuits wired in series. So, this is a circuit we've seen briefly before, but we're now going to use it to unpack some general rules about all resistors in series. Let us apply Kirchhoff's laws to this particular circuit. This circuit is labeled with the important quantities. So we have the EMF, we have the current, we have the two resistors, and we have the potential drops across them. Kirchhoff's first law tells us that because this is a single closed loop, the current coming out of the battery and going back into it is equal to the current through the first resistor, and that's equal to the current through the second resistor. And as a result, there's only one current through the whole circuit. And this is generally true for circuit elements wired in series. So for circuit elements wired in series, R1, R2, and in this case the battery, the current is the same. For Kirchhoff's second law, we apply Kirchhoff's second law to this loop, and we find, as we saw in the previous example, the EMF is equal to the potential drop across the first resistor plus the potential drop across the second resistor. So for circuit elements wired in series, the potential differences add. And in particular, they add up to the EMF. So we can generalize this for any n number of resistors. So not just one, not just two, but 3, 4, 5 of arbitrary resistances. So these can be different R's. If we analyze this relationship, we find that Kirchhoff's first law tells us that for any series circuit, I1 is going to be equal to I2, which is equal to IN. And the total potential drop across the resistors. Notice I've switched to calling this a total potential drop across these resistors rather than just the EMF, because we're not always sure what is going on up here, okay? But the total potential drop is just equal to the sum of the individual potential drops if these resistors are wired in series. So delta V total is equal to the sum of the delta V I's. So, we can use that to derive the relationship between the resistances as well. And here's our central question. This is super crucial to understand what it is that we are deriving. Here's the question. If you were to replace these two resistors with a single resistance or equivalent resistance of those two resistances, or eq, to receive the same current I, such that the equivalent resistance was equal to the total EMF divided by I. So we want to just go from this circuit to this one. What would our eq be? All right. For series, my guess is your instinct is correct, okay, in that what we're going to do is simply add these resistances. But now we're equipped to prove why that is. So why is that? The first thing we do is write Kirchhoff's second law. Kirchhoff's second law for two resistors in series says that the EMF is equal to delta V1 plus delta V2. Then the definition of resistance, R is defined to be delta V divided by I, gives us that the EMF is equal to I1 times R1 plus I2 times R2. Then Kirchhoff's first law says that there's only a single current through both of these resistors, which means that I1 is I2 is equal to I. There's only a single current, okay? And then finally, if we divide the EMF by I, we discover that EMF divided by I is equal to R1 plus R2, right? So this ratio between the applied potential difference, the EMF in this case, divided by the total current through this circuit is equal to R1 plus R2, which means that the equivalent resistance of these two things together is just equal to R1 plus R2. You just add them up. That relationship can be summarized for any arbitrary number of resistances, R1 plus R2 plus ... Rn, as the equivalent resistance for a series relationship. For resistors in series is that the equivalent resistance is equal to the sum of the R sub I's. You just add them up to get the resistor that you would replace these resistors with. Now, we're going to do a similar exercise in the next video for parallel, but the relationship between the R's is much less obvious. So I'd invite you to sort of watch or sort of take a moment and think about how you might run a similar argument for parallel at this moment. I will also give you another invitation to try to sort of execute this same exercise once we've introduced the basic properties at the beginning of the next video.